Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 9, a two-way factor model. It's a two-way analysis of variance, where we will assess interaction model assumptions on a data set with kangaroo skulls. So here is Class 9. We've got an RMD file and a data file to download. So we'll download both of those into our data analysis folder. We will open RStudio. Okay, it's already open. Go to our data analysis folder, open that markdown file, and set the session working directory to the source file, and knit the document. We'll then review the document and we'll work through it together. I will open it in the browser so that we can zoom in and read it well. Alright, Class 9, Paired Experiments and Randomized Block Experiments. This is what we're working on here, two-way factor design. So our two-way factors, we've got two factors. We've got sex and species. And we're going to use that to understand the differences between sex and species as it relates to the crest width of a kangaroo skull. We will first plot the data and understand the patterns that we see and interpret from there whether we think that there's going to be an interaction in our statistical model. We will fit that full two-way interaction model, assess the assumptions, and test for whether the interaction is significant. If it is, that is the model that we're going to use. Otherwise, we will simplify the model by removing the interaction and assessing model assumptions. And when we're happy with the model as it is, we'll summarize the differences in between sexes and between species for the crest width. Alright, so this data set has several variables, and the three that we're looking at are sex, the ones with the stars, species, and crest width. And the measurements are taken in tenths of a millimeter. That's pretty fine resolution. The sex, there's two of them, male, female, and for species there are these three, which I will probably just refer to as MG, MFM, and MFF if I'm referring to them by names. Now this data set I originally formatted years ago in a format for SAS, I think it's statistical analysis software, and the way that they represent missing values is with a period. So within the read CSV file or function, I need to specify which characters indicate a missing value. In this case, I specify two of them. If there's a blank field, so comma delimited or comma separated values file separates each value with a comma. And so if there are two commas next to each other, then that field is empty. And that's what's between these two quotes, nothing. Also, if there's just a period, then that is a missing value. And those will be treated as not available as NAs. From that larger data set, I'm selecting the three variables that we're interested in, and I'm making sure that both sex and species are factor variables, and I'm giving them their appropriate labels. Now, there are some missing values, I think. Oh no, there are no missing values in this data set. But I set up this little, these lines of code here to determine whether there are missing values and how many observations you lose by removing missing values. Now the data set we're looking at, we have already selected only the three variables that are going to be in our model. So if there are any missing values in any of those three columns, when we go to fit a regression model, it will automatically remove those observations from the analysis because you can't analyze data that isn't there. So what I've done here is I made a little sentence. I started off by saying how many rows are in the Kangaroo data set. That's the number of observation that we're starting with. Then I update the Kangaroo data set by doing NA.omit, which removes all the rows where there are any NAs in any column. Then I calculate the number of rows again, and that's the number of observations that we kept. Therefore, the number of observations that we dropped were what we started with minus the number that we kept, and I wrote a little sentence. Cat is a function that concatenates or joins together strings of text, and so I just say removed the number that we started with minus the number that we kept, and you can sort of see the numbers filling in down here, and that equals the number that we dropped, observations with missing values. So we started with 148, we kept 148, therefore there were 0 observations with missing values. So that may be handy for you later on. I believe in the next assignment I have the same code, and we actually do drop some missing values for that assignment. All right, and this is what the data set looks like. We've got sex, the species, and then the crest width. All right, so this next series of code chunks just summarizes the means and creates some plots. So these lines here calculate means in different ways. Okay, so I indicate sex with an X and species with an S. So the first line here summarizes the data set by taking the mean of the crest width and assigning that to the letter M. So in this Kang_mean, in fact that's what's being printed out here, the grand mean is 123. Okay, but then if you use a group by, you can do the same thing, but create means for subsets. So this next one, Kang mean X, starts with the data set. Starts with the data set, groups by sex, and then for each sex, it's going to calculate the mean, and then it does an ungroup at the end. So when we print out that Kang mean X, we have for each sex, male and female, we have its mean. So 111 for males, 136 for females. And that's what these other lines do too. So then I group by species, we're going to look at that one, and then we group by 2 variables, sex and species. So for every combination of sex and species, we'll get a mean. All right, so below here, we've got the means by species. So MG, MFM, and MFF. Okay, it looks like the MFF is quite a bit larger. And I guess I didn't really mention that up here. For females, females seem to be larger than males, and MFF seems to be larger than the other ones. And then this last one is where we grouped by both sex and species. So for each sex, we've got males and females. We've got the 3 species for each, and those are all the individual means. And this is what we're going to use in a plot. So let's see what the plot does. So here we've got two plots, and the only difference really is what's on the x-axis. In this first one we have sex, and this other one we have species on the x-axis, and then what we color by. So top one we color by species, the second one we color by sex. So let's just scroll down and look at the plots and not worry too much about the code, since we've seen code like this a lot of times before. So on the left we've got sex, male and female. On the vertical axis we have the crest widths. We have the 3 colors for species, and the solid lines, or the solid dots, are the means. We've connected the lines, connected the dots with a line just to visually help us connect which means belong to each species for comparison purposes. And then we also have the box plots, which summarize the distribution of each of our species. It looks like the distributions are not very different in terms of their spread. You know, there are, of course, we don't really have a sense of the sample sizes from these box plots, but where we would expect when you have much larger samples, you would possibly see a little more variability. Okay. So on the left, we see that the males on the left seem to be smaller than the females on the right because we have these positive slopes. And then for species, it looks like the red and the green are about the same, but the MFF species is quite a bit larger. So that's one way of looking at the data. Another way is to swap the colors and the axes. So now on the bottom we have the 3 species, and we have the colors represent the sexes. So males are red, females are blue, sort of opposite to our North American colors for gender. But so here we've got males are lower and sort of about the same for these 2 species, and then it increases for the 3rd species. And then for females, there's a small increase from the 1st to the 2nd species, and then again a large increase for the 3rd species. So the question here is, we want to interpret this, but also, does it appear that there's interaction? So an interaction will be present if these profile lines are not parallel. So I would say that certainly from the 2nd to the 3rd species, these look quite parallel. Between the 1st and the 2nd, it looks like there's a little bit of a difference in slope here. And so that would be an indication, a small indication that there's an interaction. This does not appear to be very strong to me. So I don't think that we're going to see it. We can see the same pattern over here. So now within each species, what's the difference between males and females? It looks like there's a slight difference between the red and the green slopes, whereas, say, the green and the blue slopes are basically parallel. So we have a small suggestion of interaction, but not very strong. So I will predict that we don't have enough evidence for that at this time. All right, let's make sure we are answering the questions. So we've got solution down here. Let me scroll up to the question. Interpret the plots of the data, the distributional centers, and the shapes. Okay, I think we've sort of discussed that. Maybe additional comment here is that the distributions for each of these box plots seems to be pretty symmetric. We got lucky. We does not look like we've got skewed data. So I'm going to expect that our residuals probably look pretty normal if each of our distributions look normal, or at least symmetric. Do the plots above suggest an interaction? We've discussed this. Probably not. All right, so let's fit the two-way interaction model. Here we have a linear model. Crest width is the response variable. We have sex star species. Now this is shorthand in R. This gets expanded into 3 terms. It gets expanded into sex plus species plus the interaction, sex : species. So this star is shorthand for the interaction model, the 2 main effects and the interaction. And I'm putting these contrasts in here because R sort of handles contrasts in a strange way by default, and if you put these in, it will allow us to make the appropriate contrasts when it comes to do that. Now I believe that this is actually vestigial in my code, but I have not confirmed it because I'm now using a different package to do pairwise contrasts, which I think does not have the problems that doing it the old way used to. But this is never a bad line to add to a linear model when you've got factor terms and you will later be doing contrasts between the levels of those factors. All right, so we fit the full interaction model. Let's check the model assumptions. So we'll use my linear model diagnostic plots function. Oh yeah, I've got sort of a crazy linear model object name here. LM for linear model underscore CW is the crest width. And then the rest of this indicates that I've got a main effect for sex, main effect for species, and the interaction between sex and species. That's my labeling convention. All right, so we look at the QQ plot. So now we're going to interpret the plots and see if we fit the model assumptions. Looks not too bad, right? We have a lot of observations. It looks like the points sort of trail off away from the line on the lower side. This actually says that we've got residuals that are a little more extreme because they're below the line than we would expect if they followed a normal distribution. So there's a little bit of possibly left skewness, but the rest of this looks beautiful. In terms of Cook's distance, this looks fantastic. We do not have like 1, 2, or 3 individual lines that are way above all the other ones. We always have this sort of background of points that are down low, and we've got about a dozen or so lines that are up higher. This looks really good. Now we've got this is a two-way factor model, so we don't have all of our variables are categorical, so they're all sort of some sort of fixed distance from 0 in terms of being an outlier in the x direction. So that's why we see these leverages appear sort of just vertically here. When you only have factors, there's basically nothing to interpret for leverage. You can't really be an outlier when you've got categories. It's not entirely true. It sort of depends on the sample sizes in each category. We have a good number of observations for each of our categories. Residuals in terms of fitted values, all these spreads look about the same. So same thing here, the variances are about the same. These look really great. Let's see, it looks like I am providing a bit more output in this case than I usually do. In fact, I don't have any additional arguments here, so the set of plots that are produced by this function by default is a larger set. Looks like there's a test here for non-constant variance, and the p-value is 0.07, so there's maybe some evidence that there's non-constant variance, but at least visually this does not seem to be much of a problem. There does not seem to be a structure of our observation over the index, so which means that this is not really an important detail for us here, and it's but if you were taking measurements over time, say you were working in a factory and you were measuring the lengths of bolts or something, making sure all your bolts were the same length, if they were all sort of say a little bit down low and then they sort of jumped up at some point in time, then that says that something in your process changed over time, and that could indicate a problem. If your data are sorted before you analyze it, then you've broken the index, you've broken sort of the time sequence of the observations, so then this plot would become meaningless. Anyway, the only time where this is really useful is when you're collecting data over time and you want to make sure that there isn't something strange that happened in your measurement process over time. The Box-Cox plot looks like there's no transformation that we need. One is within our interval here. There's a few other things that are provided here that I'm going to skip over. I guess I will say here, the variance inflation factor is a measure of how much the standard errors of your beta coefficients increase because of correlation between your x variables. So if your x variables are correlated, then that can become a problem in interpretation, because if you've got x's that are correlated, you can't interpret the effect of one of the, right. So let me start over. interpretation of your beta coefficient for an x variable is, the beta is the expected increase in y if you increase one of the x's holding all the other x's constant. Okay? Well, if you need to hold the other x's constant, you really quite can't do that if two of your x's are correlated, because as you increase one, the other one tends to increase also. And in fact, we see a problem here, but this is not actually a problem, because the sex-species interaction seems to have a high variance inflation along with species. But when you have interactions, you can't really interpret these collinearities, because interactions are multiplications between two main effects. So for sure, the interaction is going to be correlated with the main effect. All right, all that to say is ignore this plot, unless you only have main effects. All right, and then we've got some added variable plots. I'll just say all these look really great. So I think if you summarize some of those details in the solution without my narrative sidebars, that would be a fairly good answer. So let's test for this interaction. Recall visually, it did not look like we had a very strong interaction, and in fact, the p-value for this interaction is quite large. So we do not have evidence for interaction at this stage either. So we can probably, so what I would have you do here, right? So test for interaction. So write the hypothesis that you're testing, right? The hypothesis is that the beta, or the coefficient for the interaction, equals 0. That's the null hypothesis. The alternative is that it's not equal to 0. You have a p-value of 0.42, therefore, and then make your decision. All right, so because we have, we found that there isn't an interaction, now we're ready to reduce our model to just a main effects model. And so this is a point where we sort of stop just talking about it from here. Let's go over to RStudio and get to business. All right, so I'm going to scroll down to basically the bottom where we're going to reduce to the final model. And I know that I want to basically fit the same model except just the main effects. So I'm going to copy this, which is the linear model code, down to reduce to the final model. Okay, I guess I can put all this, I'll put it here. So I'm going to fit the model, and then I will do the diagnostic plots. So I'll paste that below, and then I will also do the ANOVA. And now that I've got all the code pieces down here, I will make the appropriate changes. So this will have, instead of a multiplication sign, it'll have a plus. And I'm going to rename this by removing the interaction name off of the linear model object. And I should always put these spaces around equals. All right, so now I haven't run any code in the browser yet. So I'm going to click the down arrow to run all the code chunks above. We'll get to see some plots go by. All right, all done. Now I'm going to clear the plot window over here with the broom. And I'm also going to clear the console. I usually just press Control L. And then I'm going to run each of these pieces of code, and we'll look at them either in the console or in the plots. So this first one just fits the linear model. I'm going to make the plot window larger. All right, and we'll run the plots. And we can scroll back a bit. It would also be very good to just knit the document at this point and look at that. But these residuals looks like we have a little more deviation down here. So a little bit of left skewness in our measurements. This does not look very severe to me. I feel pretty comfortable with this. Let's see if the box plot suggests anything, but I don't think that this level of deviation is going to be much of a problem for our interpretation. Cook's distance plot looks really good. No leverage issues here. All of these spreads look about the same over the 6 combinations of sex and species. Sex spreads look good, species spreads look good, meaning they look about the same over the categories. We still are getting a box-Cox transformation of about 1, so that looks pretty good. I'm not going to worry. This isn't a problem. So the cutoff for variance inflation factors, depending on which book you read, is sort of about like 5 or 10. Usually 10 is the value. So variance inflation factor of about 2 is quite low. And it really is not very meaningful for factors. So we're just going to ignore this result right here. Added variable plots does not show any extreme outliers or any observations that are changing the trends of these lines. So I think we're in really good shape here. I'm happy about those plots. And let's look at the ANOVA table. Okay, so we have 2 main effects, sex and species, and they are both significant. And I'm unable to highlight them. There we go. All right, very good. So now, so the solution down there that you're asked to wrestle with is basically do all the same stuff as before. Assess the model assumptions, assess whether the main effects are significant, or reduce further if you need to. I would say we're happy with our 2 main effects, and the residuals look great. So summarize that in your own words right here. All right, the last part is to summarize the differences in sexes and species using the relevant multiple comparisons. Let me make this a little bit bigger. All right, so I give you some code to get you started. I'm going to move this R back here by pressing the backspace key so that we can use some of this code. Now we don't have, okay, all right, so library EM means I'm going to press Control Enter to submit that line down to the console. It will load the package. So which contrasts are we interested in? Well, we have main effects for sex, and we have a main effect for species. Those are the 2 that we want to use. If we had an interaction, we would be interested in these second 2 lines, where we're interested in the differences between sex for each species, so those conditional relationships, and we'd also be interested in the differences between species for each sex. But those contrasts only occur when you've got interactions. I'm going to delete those. Just focus on the 2 effects that we've got. Also, once you run one of these, notice I've named them both the same thing, contrast _ kangaroo. So what we need is, after you create one of those, we need to create the output. Okay? So if I just create a little more space here in the code, it'll be a little clearer about what we're doing. Okay, so I now have the contrast for sex, and I'm going to show the results. And then I've got the contrast for species. I'm going to show the results. All right, let me just scroll down a little bit, and then we've got this plot. Oh yeah, so we've got this plot, which plots the kangaroo contrasts for whichever one was executed last. So we're going to need this code appearing twice as well. All right, so let's do this. I'm going to take this whole big piece of code, cut it, move it down to here with the other one, and I'm going to create 2 code chunks. what am I going to do? I'm going to take my plot. Let me take my plot code and copy that twice. And this will make sense in a second. I'm going to take the species code and move it down to the plot code in the second one. So the second one will do the species. And I'll take the sex code and I'll put that in the first. Okay, so the first one will give the results for sex and create the plot. And then the second one will give the results for species and then give the plot. I think I like that. And I remove this empty code chunk. And maybe, let's see, where am I at for, so I've got, in terms of headings, I'm at my double star. So I could do, or double pound sign. So I could do a triple pound sign here and do sex. And those are the results for sex. And then I've got a triple pound here and species. And then I just need to summarize those results. So at this point, I know that this is going to run, but I guess I'll show best practices. Let me run this code chunk. Okay. Okay, I was overconfident. Oh, I know why. LM object is not the name of my linear model object. So we have to scroll up here. Here's my linear model object. I'm going to copy that down to LM object. Just need it in those two places, one here for sex and one here for species. All right, let's run one of these. Okay, it worked. Let's knit it. Already we're getting the results of the differences between species. And this is the same result that we saw by looking at the box plots. All right, we'll go over to our browser. We'll refresh the window. So we have already done this. We've reduced to the final model, which is our main effects model, sex plus species. We were happy with the diagnostic plots. I would indicate that there's a little bit of deviation on the left tail of the residuals, that the residuals are a little more extreme than you'd expect than the normal distribution, which indicates a little bit of left skewness. Can we see that left skewness in these box plots? We should be able to. Basically, from the median downward should be a little bit longer than from the median upward. And it looks like that might be true for some of these. So I think that's where that's coming from. We also have some of these outliers down here. A few more outliers in the left tail than the upper tail. All right, we've already looked at all these. We're happy with that. All right, here is our contrast now. So the first one for sex, here we have just the means for the male and female, and the confidence intervals. Those are not really very important for us right now. We're interested instead on the pairs, which is looking at the difference. So on average, between males minus females, so males are negative 24.7 tenths of a millimeter larger than females, which means that they're, smaller by that much. And it is significant. Okay, so in fact, there are size differences between male and females are larger by 24.7. That's our conclusion there. We look at a plot of this. This plot is really tall. It's a little too tall. Let me go back to the code where we've got these figure height. So we're just looking at the one for sex. Let's just make this 2 inches, and we'll do the same thing for species 2, and we'll reknit it. All right, we'll keep going. We'll refresh this in a moment, but that'll make it a little easier to read if it's not so tall. Okay, there we go. So there's the sex one, and the red arrows do not overlap. That indicates a statistically significant difference between male and female. For species, same sort of output. Let me just jump down to the pairs. Where are there differences? Well, we've got MG versus MFM, not different. but then there are differences between MG and MFF and MFM versus MFF. So all the differences are with the MFF species. That is much easier to see once you plot it. Here's MFF. It's much larger than the other two, which are not statistically different from each other. All right, great. So that is the way to summarize this. Let me just make sure I don't want to have you do something else. I'm just paging up. Okay. Summarize the differences, if any, in sexes and species using relevant multiple comparisons and give clear interpretations of any significant effects. Okay, we've already walked through the code chunk there. That's good. There's the interpretations. You know, in the lecture notes, I have you do those diagrams where you sort of type out, you order the means, and then you give underlines. I think I still probably want you to do that. So let's do that part as well. All right, so we'll do a triple tick and a triple tick. That will give us a text region where we can make some edits. And we've got sex, we've got males, and we've got females. We have their means. So let's see if we can get these two things on the screen at the same time. It's going to be it's a little bit hard to do this when I'm recording. So let's do this instead. 111 and 136. 111 and 136. And I think I like to have those right aligned. Okay. And then we've got sort of the groups. Let me put an additional tab. So the groups here are that the males and females are different. So we've got two lines that do not overlap. If you want to make that a little clearer, it doesn't really matter. You could put it down here. Okay, so those are the differences in sex. How about species? So we've got the mean and the groups and the three species. So we want to order them by mean. Let's go over and grab their means. Scrolling down to the species. Okay, so we've got, let me just copy this table and we can work off it over here. So these are ordered sort of just coincidentally in the same order of the letters. And the means are 110, 115, and 144. And now that I've got them all down there, I will make it a little prettier. Okay. And now the groups. So the groups, just sort of going visually over here, say the MG and the MFM are not different. So that means that we've got lines connecting those two, and that they are different from the MFF. Just like that. Very good. Knit it. Write all your solutions, turn it in. We'll take one more quick look at this bottom result and make sure that I didn't mess anything up. Reload the page, go to the bottom. Looks good. All right, well, I hope this introduction helped with this assignment. In the next assignment, we're going to see the same thing, same data set, but we're going to use a different response variable. And the model is going to be a little more involved. So, see you in that one.